All right, the last talk of the workshop, we're pleased to have Auralee Edelen here from SLAC, who's going to tell us about ML-based modeling and control to enable new capabilities in beam customization.
Yeah, thanks for having me here to talk about some of this work ongoing in particle accelerators to try to improve essentially how we customize particle beams for different scientific use cases. So when we talk about particle accelerators, there's a really broad range of different types. There are really large scientific user facilities like the Coherent Light Source at SLAC, where different users come in, they apply for beam time, and then we have to deliver different beam parameters to them. There are also, large collider-based machines that are kind of running continuously, looking for new physics. And there are also a wide variety of industrial and medical applications of accelerators, which in some cases, also could benefit from improved beam customization, but at the moment are somewhat limited in that regard. And then in addition, we are also constantly kind of pushing the boundary of what we can do with particle accelerators. So introducing new technology like plasma-based acceleration to try to shrink the size footprint of these machines to get up to a particular energy. And so there are scientific user facilities for people outside of particle accelerator physics. There are user facilities within particle accelerator physics testing new concepts. And to put some idea of the scale on this, LCLS is kind of a nice example. Essentially, we have people who are looking at things like chemical processes, molecular interactions, trying to understand behavior in natural systems, such as photosynthesis, understanding matter under extreme conditions, things like protein folding. And so to do all of these things, there needs to be a very different set of photon beam characteristics for each. And ultimately, the way that we produce this is by shaping and accelerating an electron beam. And they tend to come for, an 8-hour shift, and then it's constant switching between these different setups. And so ultimately, what this requires is customization of a very complicated cloud of particles, which we describe in terms of the 6-dimensional position, momentum, phase space. And at the end of the day, this becomes a really complicated optimization and control problem that deals with a lot of nonlinear physics and also partial information. Oftentimes, we only get information about bulk scalar properties of the beam along the accelerator. And by the way, this diagram here spans a couple of kilometers, so that gives you an idea of how large these systems can be. And they're only a small fraction of the total controllable elements shown here. Things like RF accelerating cavities and magnets to shape and steer the beam. We also have a really wide variety of needs in how we set up or tune the accelerator. So we want to try to fit as many experiments in as possible, so we need the beam customization to be really rapid. We're often trying to push the beam into really unprecedented regions of parameter space, so ultra short, attosecond bunches, things like this, high currents, high energies. And then once we've established that we can achieve the required beam parameters, we have to maintain that within some stability tolerances for a long period of time. And in some cases, increasingly, users want to do things like dynamically scan things like bunch separations for an experiment. So that adds a real-time control element to it that's also challenging. And in trying to do this, there are a number of external factors that make it more difficult, as well as just the intrinsic nature of the problem. So ideally, if we had a nice model of the system, we could build a digital twin and predict easily and quickly what the behavior was going to be, and we can set up experiments that way. However, the simulations that give us the full detail of the beam take many hours on a supercomputer to produce. And then we also have lots of time-varying changes that occur that are kind of hard to identify the sources of. And then aside from that, we also have things like noise and initial conditions. So this is an example showing kind of shot-to-shot fluctuation in the initial parameters of the beam coming off of a drive laser. And so we're battling all of these different factors when trying to control these systems. And historically, we've relied really heavily on experts in a control room to set up the accelerator, diagnose issues, et cetera. And if you talk to folks in the control room, you quickly realize that they're doing a lot of different tasks that we can start to identify analogies for in traditional optimization, control, and machine learning. So things like trying to fuse physics understanding and empirical behavior, trying to ingest lots of multimodal diagnostic information, and then trying to, from pretty high dimensional signals, identify unexpected behavior or predict when something's about to fail. So there's a lot of ways that we can start to tackle each of these individual problems and provide tools that can help with the overall operation of accelerators. So in terms of just the problem of trying to shape the beam to what it needs to be, there are a variety of different approaches that we can take. So one that we've taken for a while in the accelerator community is the use of simple optimization algorithms that just look at what the present behavior is and kind of iterate towards a solution based on a cost function, things like simplex-based optimization. And then on the other extreme, we can say, well, let's try to just make better global system models. That'll give us more insight into, behavior that we can't see directly on the system. That will also allow us to use these models in control with things like model predictive control, and at least give us a good guess about where we should set the initial settings for a given experiment, even if we have to do some tweaking afterward to get it set up perfectly. And then in between, there's a regime where we can start to try to use algorithms that learn something iteratively locally about the machine behavior, and then use that to help guide the search for good setting solutions. And we've been doing a lot of work in the accelerator community very broadly on kind of each of these two approaches and increasingly trying to fuse them together. So naturally, we have started with Bayesian optimization and also algorithmic improvements of it, because this is a very sample efficient way to try to tackle the problem. So these are just a few examples up top. This is an example from tuning the free electron pulse energy. This is a photon beam that comes out of LCLS. We have done things like try to reduce the beam losses from the beam, potentially scraping against the side of the accelerator walls. And we have done some work on complicated optics tuning, where we've actually gotten pretty substantial improvements in experimental output from things like plasma-based acceleration, just leveraging pretty simple ML-based tuning algorithms. And then in terms of things that we've built upon algorithmically, we've started to do things like put in simple differentiable physics modeling into some of the modeling that we do in Bayesian optimization to help with increased accuracy in tuning and increased speed of tuning. So this is an example where we have this problem of magnetic hysteresis in a lot of our tuning problems. And so if we take a very simple differentiable model of hysteresis through something like the pre-shock model, we can then attach that to a Gaussian process model, and without doing any kind of additional magnetic measurements or anything like this, we can infer from the observed beam behavior what the hysteresis behavior in that magnet is. And then that actually allows us to have a more accurate model, which then allows us to tune up the accelerator more accurately. And so this type of approach is something that we're increasingly taking in this community. And then we've also started using things like multi-objective Bayesian optimization to try to map out Pareto front trade-offs between different accelerator beam components, for instance, and to do this online on the real accelerator efficiently with BO. I won't go into detail, but there's a pretty comprehensive review article that we worked on with the community available on arXiv that goes over a lot of the methods that we've been developing. Just to start diving into how we're starting to use more comprehensive physics models to speed up these processes. We have started using things like expected correlations from physics and injecting those into the Gaussian process model to enable essentially the expected correlations to be learned more quickly. This is an example showing that process. And that in turn translates to faster tuning on the accelerator. And similarly, we found that if we have a differentiable model, we can, in many cases, take the Hessian of that model at the expected optimum in simulation and then use that to very quickly, for a high dimensional system, find a good correlated kernel. Taking that to another step further, in the context of trying to deploy these algorithms online, it is very useful to have some sort of fast executing system model that can just be tied directly into how the Gaussian process and Bayesian optimization is doing the modeling. And so we've started exploring taking neural network-based surrogate models of systems. This is showing an example from the LCLS injector, and then using that to provide essentially prior information to the Gaussian process so it doesn't need to learn everything from scratch. And this substantially improves the optimization performance. This is showing a beam size minimization task. And if you have an accurate model, this helps tremendously. And it turns out that even if you have a model that doesn't agree with the ground truth that well, up to a pretty generous threshold, you can see this green line shows only a 40% correlation with the ground truth, we still improve over kind of naive Bayesian optimization in terms of convergence speed. And this is kind of exciting for us because often in accelerators, we do have good coarse models, even if they're not totally accurate relative to the system behavior. And so just knowing that we can even, leverage our inaccurate models to help speed up this process is really useful. As we've been getting more experience with things like Bayesian optimization and knowing that we can deploy that on these systems readily, we've started moving more towards thinking about what we can do in sort of the larger data limit and at larger scale. Bayesian optimization has poorer scaling with the amount of data, and also therefore impacts the total size of the tuning problem we can tackle. So far, oftentimes it's been applied to subsystems at a time, whether it's one part of the accelerator or just a single subsystem, like all of the focusing magnets, but nothing else. And so reinforcement learning, and in particular deep reinforcement learning, opens up this kind of exciting opportunity to be able to leverage more of the historical information from the accelerator and include more of the variables and more of the data in that process. And then also allows us to start leveraging to a greater degree more of the multimodal data in the accelerator. And there are a lot of parallels with robotics. We have a lot of problems that have continuous state and action spaces. We have a lot of images of the beam at various points. And so it's a very nice setting for starting to apply reinforcement learning. And we're starting to do this in kind of a modular way. So we're starting with simple scalar outputs, things like the photon pulse energy, and then slowly are starting to add things like beam phase space images and spectra. And one interesting thing to note here that also touches on, I think, some of what was described in the earlier talk today is that we have a lot of accelerator facilities that actually share very similar design templates. And so there is this idea of, can you design an RL agent that could perform similar tasks on different accelerator facilities and transfer between them readily? And the question there is then, how do you structure the actual agent itself to have that flexibility to kind of infer what the different lattice parameters are for the accelerator layout, and then be able to account for that. So that's an area that people are starting to work on. Shifting a little bit towards system modeling, as I mentioned, we have simulations that describe the beam behavior, but it's not perfect, and then it also is typically slow at the highest level of detail. And so a while ago, we started looking at essentially just speeding up those simulations using neural network-based surrogates. So we would generate lots of training data from physics simulations and then train models to try to execute that more quickly. And that provides then a really powerful tool for prototyping control algorithms, for planning experiments, and then also for using in online prediction and model-based control. We've actually started doing that regularly. So a number of years ago, we made an injector surrogate model for the LCLS. And many of the algorithms for tuning that we've developed since have actually been prototyped on that fast executing neural network surrogate model, which then reduces the amount of time that we need to actually use on the accelerator itself. And then in addition to that, we're starting to explore things like how do we automatically adapt between the imperfect physics simulation and how it may not agree perfectly with measurements. This is an example showing a scan of a magnet and then the beam size, and you can see the qualitative behavior is captured, but it's just a simple offset there. And oftentimes physicists by hand will go through a very laborious process of trying to identify all of the potential sources of this error and run a lot of simulations to do it. And as a result, because that is so resource intensive, we often don't end up benchmarking accelerator simulations to the real machine as much as really would be preferable. And so if we can leverage ML-based models to help us do this more quickly, that would have a pretty big impact on the field as a whole. So that's another area that we're starting to investigate. And then I won't go into detail about a lot of the different model architectures and validations that people have been doing with neural network surrogates for accelerators. But I'll just say it's a very large field, and people are working on figuring out ways to develop new architectures to deal with all the high dimensional input and output, and trying to ensure that we've validated them in a way that we can then leverage in an online control setting where we may be going out of distribution for the training data set and things like this. There's another avenue where people are looking at the types of calculations that we do in particle accelerators on a really granular level, and then trying to develop surrogates just for those. So this is an example of one of these types of calculations called the coherent synchrotron radiation effect, where essentially for every particle in the beam, if you go through a bending magnet, it will emit a photon and then hit a particle in the beam at a later point in time, and every single particle in the beam distribution, which in practice has millions of individual particles, is going to be doing this, and you have to compute that at every time step of tracking through the magnet. And so this becomes extremely computationally intensive, and it matters quite a lot. So you can see this is showing that the what we call the transverse projection of the phase space, essentially looking into the plane of the accelerator in X and Y. And if you include this effect, you get quite a different answer out of the simulation than if you don't include it. And for a lot of the really high precision applications like free electron lasers, this, although it may appear subtle difference, actually makes a huge impact in the final predicted performance. And so one thing that we've started doing is doing things like taking part of this calculation that's the most computationally intensive, and then just replacing that with a neural network that's been trained on simulation examples, and then inserting it as just a surrogate for that step. And so even if we do this in kind of the simplest version of this calculation, we end up with a 10 times faster simulation speed overall. And now we're starting to extend this to things like the two-dimensional case, where instead of having a 1D distribution here, we have an image in effect. And so there's a lot of work going on in this type of area, essentially how to fundamentally, on a more granular level, speed up particle accelerator simulations. And yeah, this is just an example similar to the one I showed on the previous slide, where if you don't include this effect, you get quite a different answer, even than the neural network solution that is shown in magenta. And the true beam is shown in blue, and you can see they match quite well. And one thing to note here is that even though on sort of an individual bit of inference, the solution is not exact because it's a stochastic process. Some of that noise ends up washing out anyway. And when tracking through a magnet, we actually get a result that ends up being very close to the ground truth. So I mentioned a little bit earlier about this process of what we call model calibration, trying to go from the simulation to matching the real machine behavior with greater accuracy. And one of the ways that we've started doing this is just by leveraging the differentiability of ML models that are trained on physics simulations. And so what we essentially are doing is forming a learned representation from the physics simulation, and then looking at the difference in predictions between what it initially predicts and then what we measure, and then back propagating that through this learned representation to try to infer, things like simple scalings and offsets. And one could start to imagine making this, a much more physics-informed process where you think about the exact types of errors you might expect beyond simple scalings and offsets on each parameter, and even starting to look at learning distributions of solutions so that you can, identify in cases where there's not a simple solution that necessarily is a one-to-one map from these inputs to the output. You could at least come up with a distribution of likely combined solutions. And so this is an area that we're also looking into pretty heavily. The same type of approach can be used with a differentiable physics simulation. So this is another major area of interest. Essentially, we are trying to develop simulations that compute the derivative when we do this multi-particle tracking through a particular simulation. This is an example from just a simple quadrupole magnet alignment and tilt problem, where these are very common types of errors from a designed accelerator to what's put in the actual beamline. And so just using a simple differentiable physics approach, we can look at the measured and predicted output beam images and then back propagate through the physics simulation to very quickly learn what the likely offsets and tilts and things are. And so now the question is, how do we apply this type of approach to situations where the physics effects are not easily able to be made differentiable? This is the case with many of the nonlinear collective beam effects, like the coherent synchrotron radiation one that I mentioned earlier. How to actually tractably make that a differentiable physics simulation is a challenge. And then lastly, even if we do this kind of initial step of calibrating to match the actual accelerator, we have this problem in accelerators where the system is always changing over time, either due to slowly drifting environmental factors or changes in the response of parts of the system. For instance, the first part of the accelerator involves a laser that then hits a cathode and then emits electrons. That efficiency of that process can change over time, resulting in a slightly different initial beam as time goes on, and it's hard to actually diagnose. And then similarly, because these systems are so large and often have individual feedback systems, sometimes we're even fighting effects of that. The temperature in the overall environment changes, so then some of the feedback systems respond to that, and then other feedback systems are responding to those changes. And so overall, trying to keep track of all of this without a really comprehensive digital twin is challenging. And then beyond that, we're also often deliberately putting the accelerator in different operating states. So this is an example where I'm showing test data from a neural network that was trained on some machine data when it was in kind of one operating state over a few days. And then we decided to change the beam setup a bit. Things like the beam charge and energy can change. And then we actually went back to what nominally was the original setup. And then just the changes that were involved in that process, there was something that ended up being out of distribution. And so then the model is no longer accurate. And you can see that this distribution shift got worse over time. And now you have a model that predicts, some correlation with the ground truth, but ultimately has quite a lot of error in it. And in this case, even though we were using some uncertainty quantification methods, the relative error is higher, but it doesn't cover the absolute error. And so this sort of online adaptation of the model and calibration of the actual uncertainty estimates is really essential if we want to use these types of models to inform decision making for accelerators. So this is another area of interest. And there, I won't go into the details, but there's a variety of approaches that we've been using to try to do this for various types of signals on accelerators. Another related aspect is, so we know we need to update the accelerator model, but how exactly are we going to do that? We don't have time to actually re-record a bunch of data from the accelerator. And so if we have methods to efficiently kind of sample the parameter space to maximize the information gain per sample, and also constrain the output to only the useful regions of the parameter space, that will help this tremendously. And so we worked on an algorithm that we have been calling Bayesian exploration, where essentially we are sampling the parameter space subject to learned output constraints. So for instance, if we have a beam where we know that it's useful to have one of the parameters in a certain range, we don't even want to bother sampling if it goes outside of that range. And so we can set that as a learned output constraint that gets iteratively updated. And then we've taken this type of approach and applied it pretty extensively. This is just one example where if one were to do it the traditional way with a physicist scanning a few parameters, that ends up being about 8 times slower than having this Bayesian exploration algorithm automatically sample parameters and then try to keep the output beam, within a useful range, but only sample to get the most information gain per sample. And one thing that's convenient about this is that even though that algorithm is operating on, like an RMS quantity for this beam size, for instance, we can save all that data and then actually fold that into learning a more detailed system model that predicts the full beam phase space that we measure. So this is an example of that, where we took data from the scalar-driven Bayesian exploration process and then folded that into a more comprehensive neural network system model that can then be used in offline control prototyping or be folded into a digital twin. Another aspect of trying to just characterize what's going on in the accelerator is the need to infer kind of complicated information that we can't directly measure. And this is another area where differentiable simulations are extremely helpful. So we have this type of measurement in accelerators where we scan a quadrupole and then magnet and then look at a screen and capture an image of the beam. And then we fit usually scalar RMS quantities to the resultant curve that we get, and then infer from this optics setup what the position and momentum of the beam looked like in this case 4 dimensions, so x, y, x prime, y prime. Instead, if we actually use the full information from the image and then couple that to a differentiable physics simulation that is tracking the whole particle distribution, we can actually backpropagate that through and learn a sort of small parameterized network that can convert an initial proposal distribution to one that is then sent through the differentiable physics simulation. And by iterating on this, we can then get a very good initial guess about what the upstream beam distribution looks like. So this is a way of getting more information about the accelerator efficiently. We've now actually extended this with the addition of another simple diagnostic, a dipole and a transverse deflecting cavity, to the full 6-dimensional phase space of the beam. So this is, that movie I showed you earlier with a beam rotating in phase space. This is x, y, z, x prime, y prime, z prime, which is something that in the past we've actually only demonstrated, I think, once in accelerators, is doing a full direct measurement like that, and it involved a very complicated setup with many different screens, and you have to move the beam through a bunch of slits, and that takes a long time both to measure and then compute. Whereas with this approach, we're able to get a pretty good estimate with just 20 measurements and about a 15 minutes analysis time on the compute that we were using. And so this ends up being about 75 times faster than the other known conventional approach, and also because of the simplicity of the layout, makes it much more accessible for many different accelerator facilities to use. And so being able to do this so quickly and get this level of information allows us to potentially improve our models online. It allows us to potentially use this information in how we do feedback control for the accelerator. So this is an exciting development. And I'll finish up here shortly, but just to give you some idea of how we're trying to synthesize these various things together. This is an example from the LCLS2 commissioning, which was an upgrade to the LCLS, where we used a detailed particle and cell simulation of the injector, which is one of the hardest, more complicated parts of the accelerator to tune, and coupled it to a local HPC system that we have on site so that we could read measurements from the accelerator, predict them with this physics simulation, and then give physicists in the control room some idea of what the machine behavior looked like, because there are a lot of signals here that you don't have access to when you're tuning the accelerator. You get information at kind of the end of the injector, but you don't get information about the evolution of the behavior. And so using this, physicists were able to get a better idea of what parameters they should be adjusting to try to improve one of the key beam quality metrics, which is known as the emittance, the beam phase space area. And then once that got into kind of a good starting point, we then handed it over to Bayesian optimization to refine the solution. And ultimately, this was what got us to kind of the best admittance value that we had yet seen, despite a lot of extensive hand tuning by expert physicists in the months prior. And so just a simple example already, people kind of imagine in the accelerator world how we could really extend the large scale modeling that we're doing, make it even faster by using things like neural network surrogates of systems, and then in coupling it even more directly to tuning with some of the algorithms I described earlier. This could really open up a lot of new capabilities in how precisely we can control the beam and how quickly we can set it up for different use cases. I'll skip this because I'm short on time, but this is just an example of essentially tightening that loop a little bit with a learned ML model. And then lastly, a lot of this requires infrastructure. And so this is actually something that I think is trying to be addressed at a much larger scale in the accelerator community now. For example, the Department of Energy, which runs a lot of these large scientific user facilities in the US, is starting to think about how can we take information from a system and then send that somewhere to an HPC system, and then run complicated ML analysis or physics simulations, and then leverage that back directly in real-time decision-making and control. And I think it was very interesting to hear the previous talk, because one of the things that they're trying to do right now is actually figure out how can they take the many different HPC systems in the US that the Department of Energy runs and make it so it's easier for any given experimental system to use kind of a centralized HPC system and be able to do that flexibly across different HPC systems so that we can make more efficient use of those computing resources. So we're, I would say, taking kind of just first steps to prototype what this type of real-time system HPC interaction could start to look like for our scientific user facilities at SLAC and beyond. I'll also just add that although we're doing a lot of work in the accelerator community on algorithmic development, we're also doing a lot of software development and trying to figure out ways to make sure that these algorithms can be transferred really readily across different facilities. So this involves open source software packages. Just two examples are shown here. And just for these two, we've used them at SLAC, we've developed some of the algorithms within them at Argonne National Lab, and then used that for experiments there. We're starting to use them at Fermilab, and even over in Europe. One of the facilities there, the ESRF, is actually using some of these tools now in regular operation. And so there's kind of on the research side, this question of how do we make the algorithms more transferable, and then on the software engineering and infrastructure side, how do we make the actual software itself transferable? So I'll end there. In particle accelerators, it's sort of this interesting space where we stand to really benefit a lot from novel AI/ML solutions in how we model and control the accelerator. That can have a really big impact on the science that people are trying to do with these machines. There are also a lot of really interesting AI opportunities for AI research as well. We have a lot of these systems where they're very nicely set up for doing domain transfer and transfer learning between different systems. We have a lot of, I would say, really interesting control problems that are very amenable to combining with some kind of digital twin or physics representation of the machine to then do really fine control and dynamic scanning over things like bunch parameters. And then because we have this kind of complicated control system environment where we have lots of human experts and many, many different types of diverse tasks, there is also this question of how do you best integrate automated solutions and tools into a system where there are, if not humans in the loop, at least humans monitoring and potentially intervening. And so there's a lot of interest in studying how we make this efficient. So for instance, if we have an automation tool that we put into the control room, we don't want that to just add to kind of the information overload that operators already have in the control room. How do you design that in a way that achieves that? And then similarly, because there's such a rich understanding of the accelerator that operators develop over many years, how do we provide these tools in a way that actually enhances their ability to prove their own mental models of what's going on in the accelerator? That's also something that folks are very interested in. So for instance, if you can apply Bayesian optimization to a part of the accelerator, it would be great if you could then easily explore the sensitivities in that learned model and then relate that to perhaps a broader physics model of the system, which would be helped a lot if we actually have a full digital twin of the system in place. So we're kind of working towards all of these things simultaneously. And with that, I'll skip this last slide and I'll skip that one as well, and then I'll end there. This is some of the team. Thank you.
Yes, thank you.
I'm just curious, how much of any of this that you talked about is transferable things like fusion?
Yeah, great question. I think there are a ton of parallels. So for instance, if you look at things like stellarators or tokamaks, this is very similar at a high level type of system where you've got, really complicated physical layouts of things. You've got kind of extreme behavior of charged particle beams. And a lot of the techniques actually for design that we use in accelerators, a lot of the same tools are used in fusion for designing things like stellarators. And then a lot of the techniques I think are very transferable. So things like reinforcement learning, obviously there are nice examples now of people using that in the context of fusion. And I think ultimately a lot of the same types of tools and algorithms are, able to be used on both systems. I think that in terms of going beyond just knowing that the same algorithmic approaches could be used, I don't know to what extent similar types of ML surrogate modeling for physics simulations could be used. It's possible that because of some of the simulations that we deal with are actually looking at charged particle beams in a plasma for plasma-based accelerators. some of those techniques may actually be very, very transferable to fusion. And I don't know the extent to which that's been explored.
I'm coming, Dirk.
Okay. Yeah, thanks a lot. Great talk. I was wondering if you could speak a bit to the representation in your models. So like in reinforcement learning, is it a black box? Is it a physics informed neural net? And you used surrogate models as well as digital twins. Like, yeah, this curious how you update your digital twin based on the surrogate model. If you could just speak a bit to that.
Yeah. So I would say, like, for the community as a whole, it's fairly early days on some of these things. For your first question, in terms of how we're actually structuring ML models that get used in things like online control and to train reinforcement learning agents, it varies a lot. Some people are using very simple differentiable simulations that we have some free parameters on, like the position of a quadrupole magnet, for instance, that we then try to calibrate to the machine and then use that simple differentiable simulation as a fast training platform for an RL agent. In other cases, we are looking at things like a neural net that is trained on physics simulations, but is treating the problem kind of like a black box other than the structure of the layout. So for instance, because it's a sequential problem predicting the beam evolution from the beginning to the end of the accelerator, we can leverage things like LSTMs to essentially propagate the beam forward. And then that ends up requiring a bit less data to train than just having an ML model that's not structure aware in the same way. And so those sorts of things can also be used to train RL agents and whatnot. And yeah, it's such a broad area that I think there are many different approaches that people are using. And then in terms of your second question about what we're actually using to, in terms of the representation to try to transfer to an accurate representation of the accelerator and keep that updated over time. So far, it really is, at least for the work that we've been doing at SLAC, very simple scaling and offset factors, and occasionally things like the initial particle beam distribution, like in the phase-based reconstruction example I showed you. That's sort of a form of this model calibration. And so ultimately, extending that to kind of the case where we could make it more transferable across systems, you might start to include things like maybe more leeway in the types of elements and positions if you wanted to, add in another parameter there to then say, I'm going to go from a model of this facility to a model of a different facility. So far it's fairly simple adjustments to model inputs and things like that. Eventually, the hope is that we would have much more of the system parameterized and be able to be adjusted. So it's a lot of work in progress.
So if I'm understanding correctly, there are some type of diagnostic elements that can be run while the beam is running.
Yep.
And there's other ones where you destroy the beam and doing that diagnostic.
Yeah.
And then at one point you were talking about the fact that you could actually correlate this information and somehow provide to the operator as that from the online information, as if you had done an intervention, what the information would be. So if I understand correctly, there's not actually any additional information being provided in the sense that it's the same information. But can you just talk more about why that's beneficial from, I guess, from the operator perspective to have that correlation, even though, again, it's not actually giving you, maybe it's giving you better visualization, but it's not actually, it's kind of fake information at some level, right?
It's sort of an interesting case where on these systems, like we have a lot of distributed kind of low dimensional information. So for instance, we get lots of information about the beam position along an accelerator. And then in some cases we have like a very detailed phase-based diagnostic at the end. Like this is from a diagnostic that looks at the timing and energy of the beam. In cases like this second accelerator here, that diagnostic occurs prior to the experimental section. And so they can't actually tune the experimental section while looking at this very nice detailed diagnostic. However, because things are highly correlated off on the machine, you can take really simple scalar information from across the machine and actually use it to predict this high dimensional information with some degree of accuracy and detail. Which otherwise, if you have an operator in a control room trying to look at all of this scalar data independently and then imagine what the longitudinal phase space of the beam, this time energy distribution looks like, that's going to be, if not very hard, maybe some very experienced operators could do it, most likely not practical for routine tuning. And the same applies actually for doing feedback control. So when we're tuning kind of this upstream section, we can look at this diagnostic and then make sure that things are set up in a way that gets the beam that we want. But then it might take, 2 or 3 hours to set up the downstream experimental section. And then in that time, there may be drifts or things upstream that actually change this beam distribution. And so without having insight into even just a prediction of what that might look like, it's very hard to keep track of that.
So the actual information, the scale information is relatively low dimensional, and you push it into this high dimensional space. Of course, you can only do that with some level of fidelity, but
Yep.
because the operator has their own mental model of what it would be, that's a better, it's almost like learning the right representation to help the operator.
Right.
Actually, in this case, literally see what's going on.
Right.
Yeah, thank you.
And just to put it in context, there can be, hundreds of signals that may make sense for an operator to try to monitor at any given point in time that have an impact on the beam. So it very quickly gets into this regime where people are just overloaded.
Are there any other questions?
Yes.
I mean, one more question. Yeah, I'm curious. So once you have a good digital twin model of your machine, it should be possible for you to use it for, I mean, maybe you did this already, to design your experiment. Like you want to measure something, and there's many different ways of measuring it. Do you sort of compute through how to actually what measurements actually should to take?
Yeah, so we're trying to get to the point where we can do that. So we're essentially slowly building out that type of capability section by section. And then in particular for these experiments that have, different users coming in, both of these machines that I'm showing here, that's the case for them. Once we have a digital twin of this type of system, in principle, we can grab a snapshot of that and then give it to them along with, potentially realistic noise distribution outputs and things like that, for them to then tweak or at least tweak their analyses processes on to help improve their downstream experiment. We're not there yet. We're trying to get to that point. And when we do get to that point, it will help tremendously for trying to plan out different beam times and also ensure that experimenters can actually collect the data that they need in the limited amount of time that they actually have on the accelerator. So moving toward that.
All right, not seeing any more hands, so let's thank Auralee one more time.